Hello YouTube and welcome to this channel. In this channel I'm providing a lot of tutorials on electromagnetic simulations, and if you are new to this channel you can find many tutorials about Maxwell simulator as well as SimPlotter that connecting Maxwell to the outside world, and you can get a lot of tons of tutorials, and I would like that you go through all the tutorials before you start asking questions that are already being described in the tutorials. And also I'm going to move on to the HFSS. Soon you will be able to see the new high frequency structural simulator tutorials, which basically is for high frequency applications. Now in this tutorial I'm going to do continuation of my previous tutorial about the transformer in transient simulations that we've done, and you saw that. And now I'm going to show you how you can create a 2D simulations of the same design that we had in the 3D, and basically compare the results. Here you have the result of the 3D simulations as you saw on the previous tutorials, and you can follow the same results in the 2D simulation as well. So first thing you want to do is you want to right click on your design, the 3D design, and select create 2D design. Simple like that. Coordinate system has to stay in the global, and make sure that you go with the ZX and XY based on the design that we've done, and press OK. That will give us a very nice 2D version of our design. And now we can create. Now one thing that you want to do is you want to go to the Maxwell 2D, and under the solution type you want to make sure that you are staying in the transient simulation, and also you want to make sure that your geometry model is Cartesian and XY. Now one important issue is when you are working with the 2D instead of 3D, you are losing one dimensions. So you have to provide that dimensions into the model, and that is called the model depth. So the model depth for the 3D design that we had was 456 millimeters. Although you might say that the core of the transformer was not like a rectangular cross section, it was like a bit like shaped like a curvature. So that will basically be what we lose in terms of accuracy when it comes to the 2D designs. But however, we want to see how much that is important at the end of the day. So again, you're gonna right click on basically what you do is you can go here on Maxwell 2D, and you under the model you go and select the set model depth. That's very important. So click on that, and now we can actually put whatever depth we have in millimeters. So as I said, millimeters is selected, and then 456. Okay, 456, and you can press OK on that. One other thing that you want to do is also, it's a good idea to change the region here and make sure that the region is staying at so right now on our X and our X padding is only 30%. That was what we choose in the 3D simulations, and now that we have the luxury of 2D simulations, we get rid of one dimensions, we can increase this padding and get a better result in that sense. So that will basically create a padding from here to here instead of 30% to 100%, which is pretty good. Okay. After finishing the region adjustment, now it's time for us to work on the excitations. Now for the excitations, when you make the 2D design out of the 3D designs, you will get some extra sections of the coil, which you don't necessarily need them. So to be more precise on that, if you go and basically look at the cross sections that we have, you will see under the copper we have LVA underline section 1 and the same for the LVB and LVC, and then we have the one that doesn't have the word section 1 next to it. If you select on section 1, you will see that it will select only one side of the sections. Those are the terminals that we defined, if you remember. And then we also have LVA, LVB, and AOC that you will see on the two sides of the coil of each core. You will see that it turns on. That means that these are the coppers that we have for the coil, and the one on the top are the cross sections that we define on the 3D sections. Now you can see that these guys are extra, so you can easily press and hold the control key and select the multiple of these cross sections and get rid of them by selecting delete. Okay, now that we have our main coils in 2D format, what you want to do is you want to again select them all and right click on them and go on basically edit, and then you go to Boolean, and under there you select separate bodies. Now that you separated the bodies, you can have access to half of them and the other half. What does it mean? That means that in the 3D designs we needed to locate a coil, meaning that there is a closed loop of material that we just wrapped around the coil, each coil and each core, and basically the 3D design will understand that there is a conducting path. That means that when you were trying to excite the coil, you just needed to have a cross sections in one side of the coil and just say run this amount of current in this side of the coil, and the 3D model will understand that this coil is indeed part of a path. There is a path, and therefore it would run the current around the coil, and you didn't need to define another side, the opposite side of the current. But in the 2D you don't have this luxury. The modeler doesn't have any idea where the current goes or comes out or comes in, and therefore we have to design basically coil in and coil out terminals. That way we can actually tell the modeler that okay, the current goes, for example, in from this side and out from this side, in from this side, out from this side, in from this side and out from this side. So that is very core, very important to know, and make sure that you are defining your currents in the right manner. One last thing is my last core is the opposite side. As you can see, the very first section is LVC or LVB, but this one here is LVA underline separate A. So that means that if I want to define all the LVC and LVB without the underline sections or separated to be like in, I want to make sure that for the LVA I'm going to do the opposite. I ran into the problem on the previous tutorial, so you guys probably know what I'm talking about. So if you don't know what exactly I'm talking about, go back to the previous two tutorials and you see the problems that we had and then how we solved that. Okay, so again, I'm gonna select LVA separated body A and all the other ones without the separations. As you can see, all the left side of the coils are selected now. And what I'm gonna do is I'm gonna assign some basically excitations to them. To do that, I'm going to basically let me just select them again and go to the excitation and select coil this time, and make sure that you're calling that, for example, coil out, whatever. You can call them assign coil. Base name can be I guess you can call it coil out. The number of conductors you can put it 76, and the sign, let's call it positive, and then the other one will be negative for sure. Okay, so that is selected, and now we should have excitation out 1A, out 1. You know what? I actually wouldn't mind if I so let's see, out 1 is A, out 2 is B, and out 3 is C. Sure, whatever. It doesn't matter. I mean, as long as it's selected the right way. Okay, so now again, I'm gonna select the LVA and then all the separates. So these are all the right side, and I'm gonna go and again go to the same process, coil. This time I want to call them in. I could have like easily That's okay. Let's just remember that 1 and 2 and 3 are representing A and B and C. Again, 76 number uh, of the conductors, and this time I'm gonna put it in negative. That means that these are going in or out. Okay, and I'm pressing OK on that, and that should take care of the assignment. Now, one important thing is you have to define boundary windings. I'm sorry, and so add windings are here for us to work with that, and we have three phases, therefore we have three windings. Again, terminals are gates, windings are how much voltage we are going to apply to that. So you basically define windings and then you assign the terminals to the windings, and you say this terminal will have this voltage connected to that. So again, let's go with that and say, okay, winding A, it's gonna be a voltage again, and I'm gonna make sure that the resistance here is 1 milli, the same as we picked the other time, and the inductance can be 0, and for the voltage we say V pick times, again, 1 minus exp minus 50 times time. That time is basically intrinsic variable for the time in the transient simulation. 2 pi times the frequency, 60. Again, you need the time, plus now it comes to the phase, and you can say they put the plus sign, I think. Yeah. Plus now the phase for the phase, actually for the winding A we don't need to have any phase, so let's leave it like that, and that should be it. Okay, and I'm gonna copy this just to reuse it again. So I'm gonna copy this, and that's basically it, and we press OK on this. It will ask what is the VPX means. It is a variable, it's a unit of voltage, that's true. And for the value, again, we come back to our specifications of our transformer, and we had a transformer that was the RMS value of 13.8 kilovolts. So that gives us the amplitude value of, basically you will have to times it by a square root of 2. That gives you the amplitude, and you divide it by, of course, the square root of 3 to give you the amplitude of each phase itself. Okay, and that should be okay. You press OK on this, and once again you have to do the same thing over and over for the winding B. So let's call it B. Again, it's voltage. It's gonna be 1 basically milliohm, and the voltage is gonna be the same, except when it comes to the phase, we will add the very first phase, which is 2/3 of the pi. That means 2/3 of pi doesn't, yeah. Okay, so we need to close this parentheses. So again, I'm gonna copy this because I'm very lazy. I'm gonna copy this and use that for the third one. Phase winding C, same deal, voltage, milli, oh sorry, milli, what am I doing here? Milliohm, and same voltage. This time I'm gonna say 4/3, which gives you the phase difference between the three phases, and press OK. Okay, cool. One mistake that I've might done is whether or not I selected the stranded here. So I forgot to say that these guys has to be stranded, because if you don't do the stranded, then it will be we cannot have the number of turns in the terminal. So that, make sure that you go with the stranded, and same for the winding B and same for the winding C. Okay, make sure you go with the stranded right there. That's okay. And so now it's time to assign the windings. A means A, 1 means A, so let's go right there. 2 means B, and basically 3 means C. Now, because we defined the directions in the terminal, so direction of the arrow, the opposite, so that's okay. You can now put again 1 into A, because it's just like a circulating current with the same phase and as the in underline 1. Again, out underline 2 has the same phase as in underline 2, but in different directions. We already did the change the directions, therefore we should be fine to just assign them into the same winding, and same with the third one. Okay, I'm gonna save this and basically call it almost over. Assigning the boundary is the very last part of this setup. Now, when it comes to the boundary, what we can do is we can basically say that the setup is the region is going to have a 0 voltage around it. To do that, just press E to select the edges, and select all the edges by controlling the tick and the control key right there, and then right click on them and say assign boundary, and go with the vector potential, and there just select as 0, so you can call it the region potential, and 0 volt should be okay, and then press OK. That's all you have to do. So that means that when the simulator comes to the boundaries, it applies this potential, okay, which is very close to the real life. Lastly, we have to apply the mesh. So what you want to do is we just want to select all the coils here, and basically assign a mesh right there, and say basically let's say having inside selection, and we want to have a length-based selection of coils, and for the maximum length of the elements, decrease it down to 100 millimeters, and you don't need to actually restrict the number of elements here, and you can press OK. So this is necessary to make sure that the simulator will create the mesh for like a good mesh for this design. As I said, transient simulation does not have automatic adaptive meshing. For more on that, you can go back to the previous tutorial and know what are the solutions that you have on hand. Okay, just because you have to always go to the excitations and basically select the eddy current effect, and leave them unchecked like that, but opening up this window tells the simulator that you are aware of this effect, and it wouldn't give you a warning anymore after that. One other thing is, when you go to the excitations, there is a core loss, and whether or not you want to select all the core losses, you just want to select at least the core loss for the core, and that is something that you have to select in order to be able to see the core loss at the end. So we press BAT and press OK on this. Now it's time to start the analysis of the setup, and you just add a solution right there. In the solution, we choose to go all the way to 0.1 second, and our step size is going to be 500 microseconds. Okay. And for the for the fields, we want to save the fields to be able to see it later on, and actually do our calculations for the core loss. And so to do that, you just select the linear step over here and say that you can start from whatever time that you want, and you can basically stop at the end of the simulations, which is 0.1 second, and you can go with the same amount of resolutions that you had on the other side, and you can easily create all the points that you need to be saved. For the non-residual, when you have an element that is has some saturation in it, and it has a BH curve, which is the core that we have right now, you need to increase the resolution of the non-linear residuals to this value in order to get the preferable results. And then you can actually save